Yeah.
All right, welcome everyone. I hope you're all energized, got your food, got some sunshine outside. We're going to start running simulations and doing post-processing. And so lead us off, I think Wuyin and Mark will give us an overview of what kind of simulations we're going to be running.
Okay, so the goal yesterday was that everybody could run an E3SM simulation. First, a 5 or 10 day short run, and then I think most people submitted a job. And so raise your hand if you checked your job this morning, and were you successful? How many of you were able to run a job overnight and see the output for that? Some? Okay, great. And we always have, whether you're successful or not doesn't matter, because you can always look at all of the run directories that we've already made. So that's not a critical part of it. So yesterday, day one, the goal was successfully run E3SM simulation. The goal today is to be able to change a name list option and confirm that you've changed the name list, and then we'll be doing analysis a little bit later today and tomorrow, and be able to compare a baseline simulation with something that you've changed. So I know we have a variety of experience in the room. Some of you have been working with E3SM for a while, and some of you is brand new this week. So if you have changed a name list before for some simulation in the past, raise your hand, a name list option. So some people, well, then it's a review. But so the simple goal for today is, for one component in E3SM, you're going to change a name list, and we have suggestions for you to change. And we're going to just walk you through all of those steps.
Thank you, Mark. So, and today I'm going to have an introduction first for the, for the general feature, or all you can do is to configure the simulation and customize in a specific way to meet our simulation design. And in the E3SM, and we've seen that's a very good practice, we recommend to, as much as possible, start with a run script, consolidate everything into a single script. Then the other change, the other customization, as much as possible, also done in the run script and save it for provenance. But of course, during the course of simulation, need to combine with some other option, including, the case control system Rob introduced yesterday through the CIME command. And some of the change, maybe when you are more familiar, you can find, oh, it's more convenient. I just manually edit it and then achieve the same objective. So that will be very well, or combination. And for this introduction and some work through some of the experiment. So my name is Wuyin, and then Chris Terai will talk about this atmosphere some namely setting. And Mark and Darin will walk us through for the ocean component and sea ice component. And then Dan will later walk through some of the naming component. Let's see, next slide. And we have a simulation yesterday, so have a quick review. We know many of you already have a successful either completed simulation or get the case created, get the job partially completed. Then this will be with this run script, that will be the typical, file structure of the case. So with the run script here is for historical simulation, including all components. The top case directory will be pointing to this one. We show that. And then this is the top case directory for the one specified in this run script. But that basically will be the case root in the script. If you want to put on a different place, just change the case root in the directory. Or if you didn't get a chance to run going, this is my test, just a similar structure. And underneath the top directory, we have this, this is a couple simulation. We have this 5, 6, including the build case script. Then this MPAS Ocean, MPAS CI is the intermediate, the driver's code. So in order to build the full model, interaction with the coupler and the run directory and the test directory. For the experience, So this one, the case script directory and run directory. So this pair, so at this top level is for the production run. Because yesterday, the final one, we look for production for non-simulation. So actually the production run, and we recommend in the future, you can also do the production run in this format. Then in the run script, just a uncommon one is production, and then change other things in the that if block or else block accordingly for the, like say, for how the simulation control you want to run, how to save the intermediate restart file, etc. Then this is the case script and the run directory, and then the test. So the test directory is for inside that one can have many tests, and each of the tests will have its own case script and the run directory. And the case script directory is no different than the one we saw yesterday with a simple, like say, case control system experiment. Just almost look about the same and has its own run directory. And test directory, there's a procedure we say usually for non-production simulation, recommend to run some tests first. Do the test usually is a shorter runs, and the shorter run, you make sure the code is built properly and the settings are as intended, and then get some short-term result to check the output are all according to the plan, and can even do some additional tests because we will have a non-simulation, we'll cover that one. You need to ensure, like say, can have reproducibility can be ensured. So these tests, under the test, you can test directly, you can do multiple tests and verify that. And among all these production simulation and the test, this build directory contain this everything after compile and link together, this E3SM.exe executable, along with the compiled module and objects, all on this directory if we use this kind of run script structure. And this will be shared by all the production run and the test run. That's also the reason, like when we yesterday do this historical simulation, the first time we said the build is then equal to true. So the first time we build the whole model, and then the follow-up test or production run, we can choose not to rebuild it, especially for our tutorial purpose. Build time take about 10 minutes. It's an expensive one. Then under the run directory, of course, run directory, you have all the history output, say from all the components. But we also have this, like say the star_in, that's the name list. That's the one for all the components and for the couplers. So that one, we'll touch that one also later. And then also have a restart pointer. File name begin with R pointer, and then each component, and then also the restart file. So get to that one a little bit by bit. So with I'm not sure. I suppose to give you a chance to review the structure, but you can do that later. Get into the top case directory to check this file structure. But in terms of customizing the settings, so this one we say mostly through the basis on the run script. So that will be for the case type. Case type can be a couple simulation or standalone component configuration. So, and the grid resolution. So this one we repeated many times during this week. And the machine for now, just the DOE machine for the permuter. And if move to other machine, that will need to do the porting work. That probably, like say, it's non-trivial thing. So need to follow some of the example and then need to do another test. Then it's the run type, and we'll spend more time on this run type. Right now, through the run script have an initial run, branch run, hybrid run, and continue run. And for the branch run and hybrid run, we usually also need to specify some reference case to branch from or to hybrid off. Then for the simulation period, so this is a general term, need to say when to start in terms of model time, how long you want to run, and then in order to manage the simulation, do you want to have, like say, just regularly save the restart time point in order to continue the simulation and other things. Resubmit, there will be next year after the job finish. Because for the supercomputer here, it has a work time limit. Like the machine we are using, the maximum is 24 hours. Then very often 24 hours is not enough for our simulation. So we need to resubmit again. So resubmit multiple times. And in order to that one to work properly, we need the restart file. And then the P layout that's related to the throughput, that's one, say per day, how many simulation years you are going to get. That's one. The other one also cost efficiency, because for on the smaller nodes, you can have some like say, oh, perfect linear scaling. But when getting to a certain, beyond a certain limit, probably not as perfect anymore, then it's a cost efficiency you can take into account. Then the other one is for the name list. And today we'll spend a lot of time on the name list. So that will be for the parameters, input data, and output data. And for the input data parameter, you can do for like say for the tuning purpose, for the physics parameters, and then for other input data file, they can set based on some other package or some other scenario, you can mix and match for these purposes. Some of them I put here, say really can say you do it on the run script, or you can even do it with the test actor, it's okay. But another advantage with this one, so for the same command, some of the parameter setting not that readable until you get familiar with that. But in the run script, we try to design each of the parameter value, make it more readable, and then translate it into the variables that are recognized by the same case system. Now we get to with the configured case, we start with the concept. Concept is a predefined what component, the mix of component into the model. So I show some examples. So this all. So basic type list here. So that's what we call it BF. This is mostly for the production, not for some testing case or for some just couple specific. I don't know for this one pop up. And for the B case, we call it the couple case. So that one, the things in the green one mean these components are active. And this is the exact component being used for this kind of active couple configuration. Atmosphere, then component, ocean, and sea ice. Then the F case is for the atmosphere only, but even though we call atmosphere only, you still have interactive named model and real model. And just to show some example concept. For example, 20TR refer to 20th century transient forcing, and we also call it historical configuration. And then the F2010, that would mean for the atmosphere configuration is the present day condition, use a 2010 year climatology forcing. And we also have I case. This is a more complicated name. So we have in the code repository log, we have described that one for what's the forcing, the boundary condition, and some additional features in the configuration. Maybe Dan later can explain more on this one. Maybe at the loss to read all these characters. And we have, like say, G case is ocean and MPAS ocean and MPAS sea ice. I put an example concept here. So it can be a G case with active ocean and sea ice. And then it's forced by a GRA version 1.5 forcing. And in this configuration, there's also a separate one that includes, like say, data iceberg, data ice shell melt fluxes. This one can have two, and then many others. Then also have C case is ocean only with the data ice, and even D case with just MPAS sea ice only. And you can find additional case information. Of course, to check for the concept, can use the query config. This one to check for the available concept, but there are very many from all component list all together. But if you like, can also look into on the code level, directly look at the XML file in that one. But also very much information in that as well. Then after we settle down on the concept for the simulation design, then it's the grid resolution. So here only just to mention, say supported for production simulation. For the node resolution, use a tri-grid, and this tri-grid is a user alias. Yeah, we see this one many times already. This is the NU30 PG2 for the atmosphere, about nominal 110 kilometer. This tri-grid for ocean and river grid, latitude, longitude, half degree. And then this one, the ICOS 30 kilometer, quasi 30 kilometer resolution for the ocean and sea ice. So this is one grid for the production low resolution simulation in E3SM. And you'll see another version 3 production simulation data is going to use this grid. The other grid is regional refinement. This one is also available, supported in the current code base, is ready to go. And later on, also include some high resolution grid there, and more regional refinement grids could also be introduced. Great. Then the model start type. So we have 4 different model start type mentioned earlier. So they'll determine. So model start type is the name, setting name in the run script. But in the case control system, it's called run type. So if you use the same command, you recognize by run type. Then in the script, you translate from the model start type to the run type. So this will really determine how a simulation is set to start. And then based on the start type, you may need to prepare some initial input data. So that input data then say in addition to the default one. And the initial type is some description is to initialize from each component independent state. There could be including initial condition prepared separately or spun up separately. But for the branch and hybrid type, will take most of the data, in particular the branch time, need to take all the state from a previous run, all components. For hybrid type, it can be a mix. You say for the, like say for the atmosphere, you can specify use the separately prepared initial condition, or the initial condition generated from a previous run. And other component, for example, the NAND, you can also bring in. So anything you specify, use the specify. Otherwise, from a reference run. Then for the continual run, you're not going to change others, just a continual run from the any type. That be after model get into stage, you can continue the simulation. For several types of the run, hybrid and then continuous simulation or branch run, the important point is about the restart or checkpoints. This will allow to resume a run, like say, oh, this run has got to be bit for bit reproducible, just like the simulation has never been stopped. So I put an example here. You have say a model simulation from the beginning run to the T10. The 10 can be 10 step, 10 hour, 10 day, or 10 years. But then in the middle, you can choose to stop at T5. For whatever reason, they say you just to schedule it, see the first 5 years, check the result. If you're comfortable, then resume the simulation. Or because the work clock, you specify 24 hours, given a TNAR can only run 5 years. Then after that one, you resubmit another one to extend that one. Or could be due to, like say, machine situation, run 5.5 time unit, then it stop, job cancelled, but then you go back to restart from the T5 and extend it. So all this one, if the model, we know the standard model is ensure reproducibility, going to guarantee that one. So all these things, as long as you use the proper restart point, going to have a before bit reproducible. And this is very common, not just for our models. And we heard, like say, even for some big machine learning model have a lot of data, then either like say need to take a long time to finish or have some unexpected event happen. We also need to design the restart point to continue that one. The concept is the same. And then for our model in particular, so for the each restart, we have the restart point with the R pointer files and then the associate R pointer file there. You can check in your run case directory. Each R pointer file will also have the file name for each component. There's a model start from that point, and then also include, we'll say the history file. History file could be like say partially accumulated. For example, we want to save monthly file, but you only simulate for 15 days. So not able to save monthly file, but you accumulate those 15 days, save there. There's a partially accumulated. And could be the, like say the not fully filled history tape. Like the history tape, like say per file, I want to say 30 days. But then each day I complete 15 days, you have 15 time slides there. So the next run, you pick up that file again, reopen it, and then add append to it. So these are the information in there. So if you go to your case directory, you can see this kind of R pointer, and then you can just show the content of the R pointer file there. So with this change, and today we will propose a list of the practice script for couple case. We saw like say the F case, B case, C case, D case, G case, I case, all these kind. At least each have one example here. And we have more for the C and D case, relatively cheaper. Maybe actually D case also is more efficient to run. So for this one with the description, say how the model is started off, for what kind of simulation type. And at the top is the link. You can also open this link to show this one is an image. So you're not able to download the script here, but we later will show, like say you can copy all the run script to your directory for further experiment. So with this one, general script, I will turn to Mark for the, like say for the namelist change and other change for the ocean and CI component first. Oh, Mark and Darin.
Okay. So for each of you, the exercise today, you can pick your favorite component, or you can pick a new component, whatever you like. And we're going to give you some choices. So the confusing thing is that the name list options appear in a couple of different places. And we're going to say this a couple times. This is at the bottom of this slide. Okay, in your run directory, the directory named run, there's Wuyin said *_in. And actually, why don't you all look at, if you had something run overnight or you had a 10-day test, it doesn't matter. Why don't you all go into a run directory right now? And we have all of my helpers raise your hand. If you have trouble for some reason, you can ask them, but you should be able to go. So there's all of your runs are on Scratch. And the alias for you personally is $, all caps, P scratch. If you haven't done that yet. So you can CD into $, all scratch, all caps, P scratch. And there's an E3SM directory in there. And so then if you do ls, I should do this here at the same time. ls *_in. Oh, this is not my computer, so that's harder. Doesn't know my aliases. Okay, so you should see all of the name lists in your run directory. So for those of you that have run other models, you may be tempted to edit those name list files. And if you edit those name list files, absolutely nothing will change, because all of those name list files in the run directory are auto-generated, okay? Because there's all of the defaults that go along with that case. That's why we do that. And so that's a common gotcha with these coupled models. And so if you want to change a name list option, there's two ways to do it. The first is to change the user NL file that's in the case scripts directory. And you can do that at any time. So if you're running and you do a restart at any time during the run, you can add the name list option there, and it's just a single one. Or in the run script, which you do at the very beginning, there's a place, and we're going to look at this in a minute. I'm just pointing out the two different ways to do it, that it actually hats into the user name list file what those changes are. Okay, so we're gonna actually take you through the details of it. I just wanted to give you that overview. Okay, so the summary is, in the run directory, you can view the name list options, but you can't change them there. Okay, and then there's other files, user name list, where you can change them, or you can put these couple lines in the run script. All right, do you want to talk about these options?
Sure. So we
Go to the mic.
So I have a couple of suggestions for doing nameless perturbation experiments. In the CICE models, we've chosen two that we know that the model is quite sensitive to, so we'll be able to see impacts. One is the changing the snow thermal conductivity, and the other is the ice ocean drag coefficient. Now I prepared run scripts for these in the path that I'm showing here. I prepared both D and B case run scripts. So a D case, a CICE only, will run quicker on fewer nodes, but by default, D cases run with the what's called a cold start ice initial condition, which is just a disk 1 meter thick ice up to some certain latitude in both hemispheres. So because of that, you'll need to run the simulation a little bit longer to get away from that initial condition. But the results will be a bit cleaner because it's only CICE active and all other components are data. Alternatively, there's also there are run scripts for a B case, a fully coupled case, which the pros there, you'd be running off a spun up initial condition. The cons are any non-bit for bit change in the coupled system is going to immediately send you onto some different ensemble member, and you'll see ensemble level variability changes in short runs. So for anybody who's interested in doing a CICE perturbation experiment, I'd encourage, well, these are the suggestions. I'm here to help and encourage that we try a couple of different things.
Okay, and of course, you all know these slides are on the agenda, so you can download them and copy these little bits of text. So for the ocean practicum changes, one of the big things that we alter often that Alice talked about this morning is the McWilliams coefficient and whether it's on or not. And so there's two separate suggestions. One is to simply turn GM off on a low resolution and see what happens. And the other one is to change the default value of kappa. And we're suggesting that you can run a C case, which is ocean only, and everything else has data components. And in this example run script, it's set right now to a 10-day run. And what I always do is run a short run first and make sure it's all working, because you can see that within a half an hour, and then do a longer run. And if you'd like to run, so I think that's overall what we're trying to do today is set up the case, do a short run, and then we'll have more speakers about analysis. And then before you leave later today, you can do a 1 or 2 year run and submit it for overnight, and then come back and see what happened. But hopefully everybody can at least have the 5 or 10 day run and make sure that everything's working, and you can check your name lists and everything. Dan.
All right, thanks. Yeah, it's pretty similar procedure for modifications for land and river. So as mentioned, if you're wanting to run just the land and river, there's these I cases, and there's one example of a run script there up top. The changes that I'm suggesting below can be added to any of the scripts, right? You can add it to an F case or a B case. The I cases tend to run a little bit faster as well. So the suggestions here, again, you can add to the user ELM in the case directory, or as part of the run script where it creates that same file. The first example, this supplemental nitro equals all. The impact of that is turning off nitrogen limitation. So essentially fertilizing every grid cell, which obviously will increase vegetation productivity. If you like phosphorus better, you can do the same thing by adjusting supple phos equals all, kind of the same way. just as a caveat, this isn't normally the way we do it. I tried to pick things that would have kind of an immediate impact. So if you're going to like look at the difference later, you could see something. Normally, if we make a change, right, we have to go through this whole procedure that I described earlier, where we take the model through these phases of spin up and transient. So the second example is a param file. So we do a lot of modifications to the land parameter file, which contains a lot of the vegetation and vegetation traits that Jennifer and I both described, and also soil parameters. And so the suggested change here is to use a different parameter file that I prepared that altered the ball bearings to model conductance slope. I think it's 50% higher. So if you use that parameter file, you get changes to carbon and energy fluxes from the vegetation. And then I noted what the default parameter file is there too. So if folks are wanting to take a look at, there's lots of variables in there, right? You could potentially experiment with lots of different things. And then an example for the river model, in this case, you'd be modifying user NL Mozart. The example here is to add this line to change the routing method. So routing method equals 2, which changes the scheme from the kinematic wave, which is a default, to a diffusion wave. I'm not quite sure what that does. You'll have to ask Hsiang if you want some details on that. And then the second page here is if you're specifically interested in these I cases, if you open up that run script, you'll see the COMSET defined there with this very long name that I described a little bit earlier. And so that the stuff that's after ELM there, that's CNP, RD, CTC, BC, that's kind of various options that are being used in ELM. And so you can change that. One example is just to remove the top, which is a topographic unit subgrid radiation scheme. And so if you remove that from the COMSET name, you can set up a run that does not have that active. Another example would be to change the CNP there that's right after ELM to just CN. And so that effectively removes the phosphorus limitation, and that should have the same impact as the nameless change setting supple phos equals all. If anyone wants to test that, they're welcome. Yeah, and I'm happy to answer any questions as folks are beginning to set these up. And then atmosphere.
Thank you, Dan. Yeah, and thank you, Mark and Darin. So we are about ready to do the real experiment. And before that one, I go back to this. I think I skipped one slide for the name list. So that would be the, like say, the file is a ._in. That's the actual name list runtime, the model to read it. And that the name list file where to specify those name list in parameter. That will through, like say, the component will have each component will have a default name list configuration. So what value to pick. And then for attribute model and river model and the NAND model will have a use case. So you can also use the use case to specify the parameter. And then the other one is to use the NL file. So among the 3 or 2 for the ocean and sea ice, the highest precedence is the user NL. So that one, whatever you specify, then you also specify in user NL, that's going to be the final choice for the simulation. So this is very powerful. So we can use the name list for sensitivity experiment, for tuning. And we are talking about, like say, today, just a 1-by-1 experiment. But the same design can be manipulated through this user NL file for all components. Like the people do perturb parameter ensemble experiment, can do hundreds or thousands of experiments, or do auto calibration, any of the component through this kind of parameter combination choice through the user NL can be used for that kind of purpose. So it's very powerful to use this user NL format. And then now we study to the atmosphere one. So let me see if I can add this link. Yeah, so that's the overall list of the run script here for the case. We saw it already. Then I would encourage you first to do this. Yeah, you can, if you don't see the URL, you can start from the agenda page, and agenda page have a practical run script. And then also from this presentation slides, can enter this page. After you enter this page, then can copy over this entire set of the run script. Use this command. I pause for a few seconds. You can do it now or later. It's okay when we can proceed with other things.
You'd like us to make it bigger so that you can see it?
Yeah. Oh, this one.
Is everybody able to access this web page? There's a link from the agenda.
Or you just type it yourself. Ideally, go to the web page. So you can continue the step there. Then we can start with the experimenting atmosphere parameter and use this run script called this AMIP. One of the AMIP simulation member, and we branch off from the year 2000. So this is the full run script. Then it's a flavor here. We specify the concept is 20 TR as the AMIP. And that's the grid resolution. We saw it earlier. And specify a case name. Try to be informative. So V3, no resolution, AMIP, and other just additional information put it there. Then it's for the code. So we say this one is for branch run as a description. Of course, you can switch this one. Given the same script, you can switch to initial or switch to hybrid. But the case not available, you cannot specify as a continue run. And as a branch run, the start date need to match the reference case. This block is for the reference case. We use the one for the standard production run for the AMIP first member 101, or the one of the member with we tag it as a year 101 as the initial condition. Then it's for the code. The code here now it's using a pre-downloaded. Just a couple days ago, use this code. At this point, if you would like, you can change this code root to the one you cloned yesterday. If you replace the whole line, but don't remember the training double quote, then the simulation will behave the same because the code at that point and the current master, they are forbid. Now it's for the simulation. So for the simulation for now, no change for this. This is each simulation type. This is each one, other than the production, these are for the small test. And we are going to choose this one for one-day simulation test. One-day simulation test, put on the custom tool, they'll set to use the 2 nodes. And right now we have S and M as like say predefined customer or predefined P&L. I think for now, just happen to be set to all in 4 nodes. So will be updated in the future. For now, if you use a target node number, just use a custom dash node number. And for this one, we reserve 2 nodes for every attendee here. So just use the 2 nodes for now. And this section will have no change. Then will be the name list. So name list will go over the other input output later. Chris will do that one. But for now, we're going to do a real experiment. So we have this, we try to say, divide it into 3 groups. So one is the default configuration. The other one with this one is ZM convection scheme. And this parameter is for the mass fraction entrainment rate. You have smaller entrainment rate in terms of magnitude because this one is a differential change with pressure. You're going up, so it's a negative. But its next smaller one will be able to have convective cloud penetrate higher. So if convection penetrate higher, then we'll expect to see more high clouds and then we'll increase long-wave cloud forcing. That's the design. And we're going to do the simulation to see that. The other one is to test with the turbulent mountain stress. So 3 set of simulation. So let's divide the group this way. We say that one's the west side, facing the ocean. We see sunshine. We pretend they say have higher chance to see convection activity. So you feel like on the west side, you uncommon this one. Just remove the exclamation point. Then you can about ready to start simulation. And later we will compare the simulation. And if you feel like on the east side, toward this one, we have Rocky Mountain on this side. So we want to play with the turbulent mountain stress. Then you only do one thing, just comment this one by remove this exclamation point on this simulation. And if you feel like somewhere in the middle between anywhere you feel like in the middle, just stay as is. Copy this script and submit it.
Can you remind me which script this is?
This one, the script is I'll go back to this page. The script name is this one. If you're able to get to the simulation page, this one's called Run with AMIP 101 and branch from year 2000. And this one going to set to build a new case and then start for 1 day, run for 1 day. Build going to take a few minutes. And then start taking action, and our other instructor and TA is going to work around. Any question, raise your hand. Can focus on this simulation first.
So should we change the namelist file now and compare this to the simulation we ran yesterday, or should we run both?
Not just one case, each group just run one. If you feel like on the east side, just uncommon the do TMS. If you feel
Use yesterday's case as the baseline to see the difference?
baseline will be somewhere in the middle, or maybe if you feel like in the middle, you just don't change anything or the submit one. And then let the other 2 sides do either the convection or mountain stress. And after that one, we will do some quick global statistics to see the difference, and you can cross-check what's the impact. Yeah.
So in the script, there's like uncomment this or comment this. Are we still doing those changes as well?
Only one. No, you are about in the middle, so no change. And just submit, don't forget, you need to submit the script. If you copy over everything, that will be this one. You copy all the screen, and then later we'll also have the experiment use this set of script. So with this one, you copy from this directory. Use this command as is.
Right, and to be clear, the instructions, these are the instructions for experimenting with atmospheric settings. So your first choice on this page is, for this afternoon, you can decide what kind of case to run. For example, if you want to play around with an ocean flag, you could do a sea case, which means that you would use this script, and then let's see, here's the right here. There's a section where if you uncomment these 3 lines, it will do one of the flags that I suggested.
We can do that later.
So step 1 is which component are you interested in? And then step 2 is you use that run script, and you can do a flag setting change, and then SH this script and run a 10-day simulation to get started. And we'll all be walking around. I think this is the practical part now of the practicum.
Sorry if this is a basic question, but the namings of the scripts, that doesn't affect what's actually happening in the simulation. It's actually what they decide. The naming is just.
It's not arbitrary.
It doesn't matter.
You can use whatever naming convention you want.
Which is you want to go to the school, but
So there's a,
Yeah, I guess we didn't say that. So for the atmosphere.
I mean, that one, they said it quickly and I didn't. Or not.
it's not spun.
Okay.
So it'll use a.
It's not on the
Both.
west side.
Or Which is fine.
Yeah, we have 100, we have 2 nodes per person.
Yeah.
I think.
I see. So this is like.
But I would assume that makes sense.
Inside of this.
So there was a question, if each person should run both a baseline case and an alteration. So we don't have quite enough nodes reserved for that. For an atmospheric experiment, the base case is what you did yesterday. For all the other cases, it's new. We haven't run it yet this week. So what you could do is partner up with somebody, if you have a neighbor nearby or you know somebody here. And one person could run a base case and one person could run an alteration, or if there's 3 or 4 people, you could do different alterations on it. Oh, okay. Atmosphere is a new case as well.
Part 2 is going to be post-processing, especially the diagnostic packages. And so Jill will start us off talking about the E3SM Diags package.
Hello, everyone. My name is Jill. I'm from Lawrence Livermore National Lab. When I'm not planning for the tutorial, I work on diagnostics packages. So diagnostic packages are a set of essential tools to benchmark Earth's model performance. And every modeling center, they have a set of tools to help guide model development. And in E3SM, we have 3 in-house developed diagnostics packages. One is for E3SM Diags. This package focuses on atmosphere fields and with some limited support for land and river variables. We have limited land and river observations in the package, but we do support model versus model comparison, as Dan earlier showed. And recently we have the ARM Diags package integrated to enable comparing model results with ARM field camping results. This can provide a process level understanding of the model. And the MPAS-Analysis is focusing on ocean and sea ice. And then the ChemDyg is for atmosphere chemistry. In different parts of the project, we also use other tools to provide additional insights and a more comprehensive evaluation. So I listed some useful resources here for E3SM Diags. First is a GitHub repository and the documentation with quick guides. And I don't know why I listed the repository again. And a reference paper for our GMD paper from 2022. We have a lot of contributors who contributed directly or indirectly in the data development and the code development. Brief introduction. This is a Python-based open development project. And we have E3SM Diags implemented in our post-processing tool Zippy as a standard analysis task. And in our version 1 of development, it's modeled after the NCAR's AMWG package, which is commonly used and known in the CIME community. And we focus on atmospheric component and also start to expand capability for land and river. We are maintaining an updated observational data set and keep them updated when new data resources are released. This package accommodates CIME variable convention, so hopefully it can be used as a community tool beyond E3SM. Some technical highlights. So this package is very flexible to add new observational data sets and diagnostics, and also it's easy to modify the figures on the fly. And it runs fastly using multiprocessing, and the provenance are saved for reproducing the diagnostics results. We follow Python best practice And it is common for most of our Python projects within E3SM project. And on this slide, we listed those basic sets after the AMWG diagnostics package. And these plots you may already feel familiar. So for instance, for the first plot, we have three sets, three panel plots. The first upper for the middle for the reference data, and the bottom shows a difference plot. So the middle can be an observational data or from another model run for model versus model comparison. And in the table, I listed all the observational data sets available, but the fonts are probably too small, but you can look later. So on the bottom, I listed example command line to produce one of these three panel plots. So this is a minimal unit E3SM Diags can produce. So in the exercise, I will ask you to looking for this command line so that you can use them to reproduce one of these plots. In some new sets included in version 2 of the development. So I listed here, including the INSO diagnostics to show the relationship between the atmosphere fields and the SST anomaly, the Dino cycle phase and the map plots for precipitation, the QBO diagnostics, the stream flow diagnostics, and the newly added wave number and frequency diagnostics here. On the right, I show some specialized examples. These four are from ARM Diags, showing the cloud diurnal cycle of each month and showing some aerosol cloud interaction metrics. And particularly for this one is contributed by Xiaojian Zhang, who's also in the audience. And he did a summer intern with Loris Livermore and implemented this very nice set. And on the bottom showing example from TC analysis. This is more useful for high resolution model evaluation. Yeah, and you can see that these analyses are all from previous papers or studies or other packages. But what we do is to translate them into Python and then put them together in E3SM Diags so they can be run streamlined. And other aerosol diagnostics metrics recently being added to support the E3SM aerosol working group mission. Their mission is to reduce the aerosol bias. So I'm not going to go through every of them. And we do have a rich set of observational data sets and reanalysis data sets included. And the data selection is guided by mostly NCAR's climate data guide, and many are recommended from scientists and from the journal articles. For the data processing and the generation, some data are taken from PCMDI's Ops4 MIP project. They distribute data for ESGF, and others are downloaded from individual data portals, for instance, from NASA, NOAA, ECMWF, and ARM data archive. A little bit more about the CIME data support. So we support CIME variable name convention in E3SM Diags. And Chris Golas generated a workflow to run E3SM Diags across all the CIME6 models. And we created this web page to host all the results. So one can compare E3SM Diags results with other CIME models. I provided a link here. You can view the results later. And the box plot for root mean square error, you have been seeing multiple times earlier, I believe. A little bit of ZP. I believe Alice and Hsiang-He will be also touch up on ZP. So this is an end-to-end diagnostics workflow we developed to facilitate running all the diagnostics packages. So it handles those common analyses from NCO, MPAS-Analysis, and E3SM Diags, and handles the dependencies under the hood. So if you are interested in running multiple diagnostics packages and you have a very long simulation, you want to apply all the packages in multiple year increments, and the ZP might be a better way to run all these diagnostics. And some recent features we added, including the IAM benchmarking system, and we also now support plugins. The ChemDyg, Hsiang-He will be present later, is an example of the plugin. Tomorrow, Ryan Forsyth will have a very more detailed description of ZP, and this is just a very high level overview. Future work, we'll continue to add new sets. So please let me know if you are interested in contribute. And we plan to support short-term averaging and visualize unstructured data, perhaps through UX array. And there's some technical update ongoing. We are migrate towards X-array and XCDAT to replace CDAT, our old library for data IO and manipulation. Okay, now that's how to run the package. So firstly, I want to emphasize E3SM Diags only supports data on regular latitude, longitude grids. We don't support raw E3SM output for now. So the practical intro Charlie provided will be very useful here. We will need some pre-processed data to generate the seasonal climatology or monthly time series. I just play some pseudo code here. And so for installation, you don't need to worry about it now because you can access the package from E3SM Unified. But in your home institution, you just need to install the packages through Conda or to grab data from our data server for observational data sets. So how to run? In this slide, I provided an example of the run script of E3SM Diags to run a basic set of diagnostics. It's a Python script, and all the parameters are passed in with a parameter object, and then the parameters are pretty basic, including the reference data path, the test data path, and the test name is most oftenly your case name for the simulation, and you can have an alias as a short test name for it. You can specify season, the number of workers for multi-processing, and then calling E3SM to run with all the sets listed here. I also listed a much longer script for an extended run and linked it here. And I also provided the output results and all available parameters that you can use. So running E3SM Diag standalone has its benefit because you have more parameter options exposed to you than running with ZP. The quick guide on parameter. First is to download the tutorial example, use wget, and edit the script with your directory that you have written permission, and ask for interactive nodes. Then source our favorite E3SM unified environment and run the run script with Python. You can go through some output example here, which is pre-made. And now this is the end of the talk, and the practicum is showing up here. Basically, I have two sets of practices. The first is to run E3SM standalone, to run a model versus ops case with existing simulation. And the other one is to run model versus model. So you can compare the existing simulation with your own simulation. Hopefully you already have a 1 year long simulation ready to play with. And the second case is running E3SM Diagnostics through that ZIPI. This is a homework, so maybe you can practice it later at home. And so here is the markdown for the exercise with solutions. So please enjoy. Any questions? All right. Yeah, that's it for me.
Yeah. Thanks, Jill. Next, we have Alice. This one?
Yes,
Is that right?
thank you.
So Alice Barthel is back, and this time talking about the MPAS-Analysis.
Thank you. I do want to acknowledge this is going to be a very quick overview of MPAS-Analysis, which I subtitled an introduction for everybody. And all that I'm presenting is really the work of a team of MPAS-Analysis developers and contributors. So the scope is a brief introduction. What is MPAS-Analysis? How would you go about running MPAS-Analysis? I might show you some of the key plots that are kind of the go-to plots that oceanographers start with to assess a simulation. There will be a slide on troubleshooting, which I hope you won't need this afternoon, but who knows? And a note that you can do a lot more. So in short, MPAS-Analysis is a condat package that has been written to perform specific analysis of MPAS Ocean and MPAS Sea Ice. It tends to generate lots of plots. It brings it up in a HTML, like you can just have a path that is publicly accessible online. And these plots are all sort of predefined in the package. So it's a really good way to have a kind of single command line way of producing sort of your basic analysis for a new simulation. Examples of the plots that get produced can be climatologies. So this here is an example of a 50-year climatology. You can see it in the title at the very top of sea surface height. And you have the top panel is your model result. Your middle panel is an observational data set. This here is the visodynamic topography. And then it does a difference plot at the bottom, the model minus your observational data set. So it does the climatology of the model results for you, and it does regridding to be able to compare to the observational data set. The other kind of major plot that you might see is an example here of, let's say, a time series. So this is sea ice area. So this is for the different component, the sea ice component. And what you see in the x-axis is time, in the y-axis is your sea ice area integrated in the northern hemisphere, so your Arctic sea ice area. And the wiggles are just because this is a very long time series, and the wiggles are the seasonal cycle of having a lot of sea ice in the Arctic and then a low sea ice in the summer. And what you see in blue is the range of the observational climatology of Arctic sea ice. So these are kind of the two major types of plots that you might see if you click on the link once you've run MPAS-Analysis. It's developed and maintained by many people. Here are some names of kind of the primary contributors. The code for MPAS-Analysis is available on GitHub. So if you want to open it to actually know what the different functions and different plots do, that's a good place to look. We do take suggestions and contributions if you're very keen to add a particular analysis or a new plot. The infrastructure for it is a little bit challenging, and we ask that, yes, we do take contributions, but we're also don't have infinite time to add your favorite analysis. So there might be a bit of a process as to whether we think this is a first order plot, but please, you're welcome to give feedback or reach out to us. There are very much more comprehensive documentation and video introduction tutorials that I invite you to look at. In short, for sort of today, what you need to know is that running MPAS-Analysis, kind of, this is the workflow. You start with an input. This is going to be a config file, .cfg file. This particular config file that I put in bold here is the part that you get to edit. And you get to add, kind of like what we're talking about with the name list options, you get to add the things that you change compared to the default. So it relies on all the other options being defined elsewhere, and your little user config file gets added to that. It relies on having the right environment, having pre-processed observational data set. But in short, you edit a config file about which year and which analysis tasks you want to do. MPAS-Analysis does a lot of things under the hood as parallel tasks to average and generate your climatology files and generate some plots. The outputs that you can look at includes the post-processed data that you can find, the .nc, the netcdf files, plots that you can find, again, locally, or that you can find just kind of the pictures displayed in an HTML path. The main part I want to make is that you can edit the input in the login node. You can look at the output in a login node or an internet browser. The middle, there's a lot going on under the hood. You do not want to run MPAS-Analysis in a login node. You want to run it on a compute node. So part of the workflow will use either sbatch, which is submitting a job to the queue, to the scheduler, or salloc, which is asking for an interactive node before you run an MPAS-Analysis command. So if you're going through the workflow and you use neither sbatch nor salloc, yeah, you might get slapped on the wrist for overwhelming the login node. In short, your config file is going to look like this. This is just excerpts from it. You have different sections that you can see with the square brackets. And under each section, you edit a particular variable. Again, you don't need to edit all the variables. What you're editing will be added to on top of the default. And you have sections like input, output, and then you have sections for specific tasks. So something like start year or end year, you're going to see it maybe once under the climatology task, once under the time series task, and you can use different combinations of start year and end years. So once you've run MPAS-Analysis, which you will get to do very soon, the key plots that we tend to look at to evaluate the ocean state. You generally start with some of the big picture climatologies, SST, sea surface temperature, sea surface salinity, sea surface height. In particular, you're looking at long-term climatologies compared to long-term observational climatologies, just to check, does this look reasonable? Is the climate roughly in the same space? You can look at time series of transports in particular locations. So you see here, you have a little inset plot where you look at, this is the section that we're looking at. This is the Drake Passage. So you have Antarctica to South America. And those transports are nice because you have the transport calculated time series in black, and then you have the observational range. And again, what we're looking for is, is this of concern? There are some where we don't have as many observations. There are some where we know the model kind of struggles to have as high as transport as observed. But these are usually just a good sanity check to have. Other things that we have observations for, as I already mentioned, is the time series of sea ice area. Here you can see the nice seasonal cycle. In black is your simulation. In blue is the observed climatology. And then you have a whole bunch more plots. The AMOC stream function, not observed, but we have a sense of what it should be looking at. Like ocean heat uptake. If your model is having very, very large ocean heat uptake as a function of time, That's something to notice. And then if you're running something, let's say over a historical period, you might want to look at coupled variability like ENSO. This is your troubleshooting slide, which hopefully you will not need. There are different types of errors at different stages of the workflow. You can have an S-batch error, in which case you might look at your options for the job submissions. Then you can check if it's submitted successfully, you can check the job status, and then you can check individual logs. And this is more for future reference if you need it. MPAS-Analysis can do a lot more. It has a lot more options, more like over 1,000 options. You can, if you're curious, read through those files. It has extra, you can have a model-to-model comparison. And it can also be run, what you're going to practice today is running it on its own, but it can also be included in Zippy, which you'll hear about tomorrow. And so for the practicum today, you're going to have an hour in total to look at the 3 different analysis tools. So maybe aim to spend 15 minutes, maybe 20 minutes on the MPAS-Analysis practicum. And then if it's something of interest, you can maybe spend your extra time on it. I provided 2 sort of straightforward, hopefully, exercises to run with the troubleshooting instructions if you're having difficulties. And I would encourage everyone to try those exercises. And then there are additional optional exercises if you have a specific interest in the ocean or in MPAS-Analysis, or if you have time and you want to look into it. So the link is up there. The link is also a Confluence page that's on the agenda. And hopefully you have step-by-step instructions. So I'm happy to help anyone when it comes to that.
Questions for Alice? Next up is Hsiang-He will be talking about the ChemDygs and giving us an introduction of that.
Hello, everyone. My name is Hsiang-He, also from the Lawrence Livermore National Laboratory. And the benefit of being the last speaker is just the previous 2 speakers that covered the most of the how you run the diagnostics that goes through which process and which kind of tools that you use there, etc. So for me, I'm going to introduce you the kind of E3SM chemistry diagnostic package. So it's a ChemDyg. And so simply, the ChemDyg is working for the E3SM chemistry part. So we are just provide you some observational data or analysis data to help you to 2 purposes. First, you just evaluate the model result. So that's the kind of all the diagnostic package. The first that provide you the benefit. The second, if you want to do some specific diagnostic like QBOI or some ozone along the stratosphere and the troposphere exchange flows. So like the kind of specific diagnostics also ChemDyg can provide for you. So the first that we are trying to introduce something. Okay, too many monitors, and so we have a input data. So it's covered like the NOAA's surface ozone and the typical our previous versions, the E3SM V2s, their chemical data, and also some map you probably need for the convert from the negative degrees to the long grades. And also we provide some ozone holes observational data, QBOI index, the surface ozone analysis. So just somehow that we consider that's a very available observational data that can do for the model evaluations that we all add into the ChemDyg. That's the purpose we use here. And so since those we can see a lot of the improved data. They also sometimes, some of them are kind of monthly, their average mean, and some of the kind of surface observation can be the hourly basis. So also we also kind of require that when you run the E3SM, you also need to like default monthly means their output, and also need the monthly instantaneous output. Like I mentioned here, is you have the, I think the for your when you run, there's a tool. Okay, never mind. So you can see that you have requires the different monthly data and the daily outputs, and for certain specific comparison, and also the hourly data, for example. So here's I would just like to introduce you some of the basic model evaluation. And so when you successfully run the ChemDyg, that you will get the one simple HTML kind of web page interface. So it will show you all the diagnostic plots on this page. So then you will see the okay that long really cannot work. Okay, so you can see the line long plots like for ozone, and also the ozone time series compared to the CIME, the other data sets. Surface ozone compared to the observation, and also the COs compared to the observation as well, and the ozone holes, the diagnostic. So those plots, the purpose that you just see when you run the models, that, oh, okay, does the result looks reasonable? And so that's why when we run the diagnostic, there's some key points, key variables that we are looking at is, oh, is it fit in the kind of reasonable range, and compared to observation, compared to the other reanalysis data, it looks fine. The second part I mentioned, the specific diagnostic, like when we want to run the QBOIs, for example, and so that's kind of one of my colleagues, just kind of to create the QBOI index. So that's why is that when you run the ChemDyg, that you can gather those QBOI index to see the kind of further diagnostic and further study for the QBO. And there are others like ozones, the ST plots, and this is ChemDyg also can provide you some specific line long plots and a monthly basis. And that's the kind of other diagnostic that could not present to you, and ChemDyg have like kind of specific strengths there to run this kind of diagnostic. And the specific part for the, or I should say that originally is when we designed the ChemDyg, as for the chemistry developers that can have their kind of tool knows what exactly which process when we do the chemistry develop this, maybe something wrong, because we know the chemistry is actually quite complicated process in the Comeau model, and then you have to kind of explicit the process, implicit process, and also have the emission, deposition, dry deposition, wet deposition, etc. So sometimes you are gather the kind of ozone concentration, for example, or it just doesn't make sense for you. You just say, why I got this wrong number for ozone concentration. And but you have a trace back that maybe in the certain process it has something wrong, but you have no idea, especially for also model developer, and you want to trace back which process actually might give you that kind of problem. So that's why when we designed the ChemDyg, we even just the purpose of here is actually is to calculate each tendency. So we know from the emission and do the explicit solvers and do the aerosol cloud, aerosol gas phase conversion and do something else. And each process that we can look at those tendency and understand, okay, there's a loophole and there's a problems and we can go to fix it. Of course, there's a kind of big table, complicated numbers, and that's only for developers, especially chemistry developers, to look at dig in to those processes. But for you guys, probably the previous two actually can give it to you kind of big picture for how the chemistry works. So So here, so running the ChemDyg is actually is quite simple, and that's why I say the BLS one actually is quite easy, because you can just download you see the E3SM unified and the ChemDyg already building inside, and you just grab the one script, run script. I also provide the one example script for you on the conference page, so you can go on and to download it. And this one, since the ChemDyg have to run through the ZP, the DP of the ZP is actually will be give you provide to you tomorrow. But you just see it's just one simple comment, ZP -c, and then you just run script, and you can get your results immediately. And so when you look at the example ChemDyg script, that should look like this. Just remember under give you input data. I already provide you input data, should be okay. And just your output data should be under your folder. And also you should have the WW to look at your plots. So those are two, remember, have to change. And the rest of the part that you can keep it if you want to play with the different years, something else. I think that right now, so we have the 15 years for you, and you can just see I want to look at 1 or 2 years, it can run faster, and then be totally fine. And also, so first the one that actually this one, which is because the ChemDyg, like I mentioned, is from the negative, like E3SM negative grades, I have to convert to like a climatologist data or the time series data. So let the first part of this page actually show you it's just how later pre-process when you really go into the ChemDyg. And the second part is just right now the ChemDyg provide to use 12 different kind of the plots and 3 tendency table. And this is a kind of 15 list on you. So you can just, a user can easily see, I only need one to, like I only want to see the ozone hole. And then you can just kind of look at the ozone hole, and then you can ignore the rest part. And or you just want to see the whole all of it, and it's individual script and run submission. So that will be other useful resource for you, and you can feel free to look at, and also have the the papers, the description, so they will tell you the details of those plots. Okay, I think that's it. Any question? No, and we have exciting to start running now.
Okay, all the speakers will be available, and other developers who have the experience with the packages can also help with the practicum. So feel free to let us know if you run into any difficulties.
Does anyone have any questions regarding accessing the agenda material of these slides? It should be on the agenda and so forth. So I think the big thing, especially with Zippy and MPAS-Analysis, is make sure you run on request and interactive mode when you run these, because they are computationally expensive.
Yeah, and all the instructions are included in the practicum. If you find it in the agenda, the practicum will have the explicit options. There were 2 modifications made to the MPAS-Analysis instructions. One of them is a typo, whether it's a WW or it shouldn't be at the end of the exercise after you've run things. If you're opening it in your browser, it's a slightly different address than if you're opening the path. And then there is a permission command, cursive permissions to the folder. It's also included in the new version on Confidence. So maybe reload the Confidence. And there's an extra command line permissions. And then the modified HTML.
What's your okay.
I hope everyone had a chance to run some of the packages, and You can also take it home homework as well. Too. Not today, but once you go back to your home institutions. But before we go through the recaps, Wuyin wanted to mention about running today's long simulation and some ideas. Yeah.
And again, yeah, so this one, we still have the reservation until midnight. So we save the best for the last. That means we want to keep the machine work hard for us while we go for fun or for rest. So that we want to keep the machine work hard. And yesterday we know for the historical simulation, I think have some echo. Historical simulation, somebody probably complete 1 year, some maybe just complete a few months. Somebody that job probably never get a chance to get in. So I've seen the 3 scenarios. You didn't run the script or didn't even get to build. Yeah, so can just use this script. You can copy over from the case. This one slide is on the agenda, so you can download and copy this path, run the script from scratch for 1 year simulation. Or if you catch the case build it yesterday submitted, but its execution time is beyond the reservation window, so it was never really run, then you will have the production case script directory. Then you can go there, just submit it for a non-simulation, but with this format, change reservation to day 2. Yesterday's script still reservation day 1. And a third scenario, so this is some kind of new case we haven't, like say, gone through today so far. So that will mean to continue the run. There for this historical, that will mean you run a few months, but then time out. I heard somebody run 5 months and then time out.
That's me.
Oh, okay, yeah, so that's good. And for this case, they carefully check a couple of things. You can go to your run directory. If you use the script, there will be this directory here. And you check the R pointer files. So I take the example for the driver is a coupler. Other components are similar. So you look at the R pointer file.erv, it will show format like this one. It's 2006. That will be beginning of June. You could write the middle of June, but then this one, the beginning of the month, there's the pointer file there. From this one, you will know complete 5 months. Then to complete 12 months, 1 year, you need to run another 7 months. The first step, go back to the case script directory again, need to change the continue run to true. Initial setup is false, so you resubmit it to start from month 1 again. So this is necessary. And then you change the stop option. That means how to apply this, the names is a unit. The default script is a number of years. So we change to number of months and then matching this number. So basically it's this number with this month number in -1. Plus together is 12 months. Then the same, resubmit it with reservation 2. If any question, then we can just for a little while can ask a quick question for this scenario case 3. Other than that, today we already have a practicum go through, have other case, then you already test for some shorter simulation, and you are interested for longer simulation, just change the run type to the production run, or customize that one, change for a longer simulation, either multiple months or even multiple years for some fast cases. You can follow the script here, have a description, different cases, or in the slides went over earlier today. So that's all. Any quick question, our TA will be here.
And Ellen pointed out, you might, if you do run into an error with this, if you are to modify yesterday's case submit and you hit an error, you might need a change. Just likely not need this, but you might need to add that as well.